yeah, we renamed our group recently because we thought that after Thomas left, the focus of our work has shifted and will shift a bit away from the pure theoretical analysis of execution models and a bit away from the hardware, more towards application developments and supporting scientists. And our goal is to enable scientists to do science they can't do today. What's stellar? Well, it's pronounced stellar, but it has actually a meaning. It stands for Systems, Technologies, Emergent Parallelism, and Algorithms Research. So that's what we think we will focus on in the next couple of years. Everything we do is certainly still centered around the parallax execution model and around its implementation, its experimental implementation in HPX. HPX is an experimental runtime system written in C++ we use and where we implemented the ideas of parallax. And that's the basis for our work with regard to helping scientists to rewrite their applications in more efficient ways. So we are very application driven and we want to enable new science, as I already said. Very quickly, what's HPX? Well, HPX stands for High Performance Parallax and is a runtime system implementation which even if parallax is targeted at future architectures, at machines as we expect them to be in 2020, we have to start today to program those machines and to build systems or software for those machines. And that's why HPX is targeting conventional clusters and conventional multi-core machines so that we can start today to write programs for systems we expect to have only 5 or 10 years from now. Currently, HPX is a mainly software-only implementation. Actually, it's almost 100% software-only implementation. As Ram this morning mentioned, we have Marshe working on special hardware which might speed up HPX and help make HPX more efficient. I'll get back to that in a minute. Well, the emphasis of HPX is mainly functionality. We are trying to do something completely new. We try to overthrow the conventional way of doing programming. And since we do something very new, we just don't know what we are doing actually, right? And that's why we try. We have to find the functionality we have to expose to the user. We have to find what's the best performance. How can we leverage the multi-core systems we have today? We have to find the best APIs. How can we provide that software environment to the mere mortal scientist who does programming just to solve his problems and is not a skilled computer scientist most of the time. And certainly HPX is driven by real applications. We want to do application work, and we have some implementation of adaptive mesh refinement algorithms, contact. Those two, by the way, you can watch in the demos and in the hall outside, where you can get a glimpse into what we are doing actually. HPX should be retargetable. As I said, it's a implementation for systems we have today, but it should be usable tomorrow when the new systems emerge. So we try to build a very highly modular system with C++, which gives high performance on one end, and on the other end allows us to modify the system and the runtime system very quickly for new architectures as they emerge. Well, if you look at applications as we have them today, then you will notice that there's a whole group of applications which are just, I'd say, performance impaired or scaling impaired. That's applications which run perfectly fine on a single core. They might even run in parallel on 10 cores or on 10 nodes or even on 100 nodes. But most of the time it's you can add more resources when running that application. You can run it on 200 or 1,000, of course, but you don't get any performance gain from doing so. So they are just plainly performance impaired or scaling impaired. They can't scale with when you throw more hardware at them. And the reason for that situation is what we call the four horsemen, or slow. Well, the first is starvation. That means if you have not sufficient parallelism in your application, you might throw many resources at it, but half of the resources will just sit idle because there's not enough work to be done at the same time in parallel. So half of the system is starving. Latencies. Latencies are the time distance delay of remote resources. If you have a lot of communication going on, you have to account for the time it takes to get for a message from A to B. And usually how systems or programs are written today, the core is just sitting there and waiting for a certain communication to happen. That's where the latencies. That's why latencies are so important to be defeated. Overheads. Overheads means if you add parallelism, you somehow have to manage that parallelism. If you have lots of things to manage, you have to do more work to manage those resources. And the backside of it is you don't have to do these overheads, or you don't have to do that management if you run in serial code. That's one of the problems when you add parallelism, that you usually add so many overheads to the system that again it slows down the whole application. And the last of the four horsemen is contention. Contention stands for just oversubscribed resources. If you all heard about the memory wall or other walls in today's architectures, and if you do too many things on the CPU, for instance, the CPU can't cope with the amount of work it has to do. Or if you have too many memory communications going on, the memory can't cope with the speed, which slows down again your overall computation, because parts of the system are contented and the other half of the system is just idling and is starving. So that's our quest to overcome these four horsemen, which essentially are the cause for our performance impaired applications we have today all over the place. The bottom line for all of that is that these four factors impose an upper bound for the scaling of our applications, and we need to do something about it. Okay. Straightforward from there, just to give you a sense what HPX is actually there for, is very easily answered, because it has to implement all that functionality you need to remove starvation, to hide the latencies or mitigate the latencies, to reduce the overhead, and to resolve the contention. Well, 1, 2, and 4 are more or less straightforward to solve. But the more you do in terms of defeating 1, 2, and 4, the more work you have to spend on 3. So our current situation is that we are quite nicely able to mitigate latencies, we can manage parallelism, but we add so much overhead, because we are software-only implementation with HPX, that part of what we gain from parallelizing and from making applications more efficient is lost, because we have to do a much more work in terms of overhead in the system. And that's something where the hardware comes in, where Marche plays a central role, because we hope that by moving part of that management work, which has to be done, into the hardware, same way as 20 years ago, many of the virtual memory things have been moved into hardware and nowadays are in mainstream hardware just implemented. The same way we want to implement part of the parallax idea in hardware, just to get rid of the overhead as well. Well, what's parallax? You all heard about parallax. I don't know if you have a full understanding of what it's actually doing. I just want to do a kind of superposition of conventional way of doing things and of the way how parallax tries to approach these things. Well, the current status of doing distribution of data in a large distributed system is called PGAS, which stands for Partitioned Global Address Space. But we think that it's not sufficient to do proper parallelization and proper load balancing over the system. So we invented something which is called AGAS, which is Active Global Address Space. So we do Active Global Address Space instead of PGAS. Our model of computation is message driven instead of message passing. What's the difference? You might say, hey, it's just a word, it's probably the same thing, but there's a fundamental difference. The current model is based on message passing. That means when I send some data from one node to another node, the message is passed in the sense that the other node has to know when will some information arrive. So it will sit there and wait. Okay, wait for the piece of information to come over. And only when the sender actually sends the information, both parts can go on in their computation. So one of them is just sitting there and idling. It's not doing anything because it's waiting for the message to come in. What we try to do, we want to do message-driven computations. That means that I just send off the data or the work to another node, and the other node doesn't know that this work will come in, and will just react to it in time when the message arrives. So no time is spent on waiting, on idling. We want to do lightweight control objects instead of global barriers. Current implementations or programming models have some lockstep method. If you know about how these simulations are done, it's usually time stepwise, right? You evolve your physical, your model in time stepwise. And as it's implemented today, you often have the case that you do one time step, then all computation waits for that time step to finish, even if part of the computation already is faster computed and part of the computation still is going on. Everybody will wait for everybody to finish that time step, and only then you do the next step in your evolution. That's what the global barriers are. But most of the algorithms, if you analyze them, you will see that there's only a constrained dependency you need to fulfill in order to go forward with one of the data points. You don't need to wait for all of them, you just need to wait for the neighbors, usually. And that's where these control objects come in. Latency hiding instead of latency avoidance. All the effort in MPI today goes into making message passing faster by optimizing the networking layer, by doing a lot of tricks. But most people now realize that it's much better to overlap computation with message passing. I mean, the network is completely independent from the cores. Why not do networking while the cores are doing something else? That helps us. And so on and so on. I just don't want to go on too deeply because I run out of time. So there are a lot of things we just want to do the other way than other people want to do it. And sadly, that leads to many problems when you want to do publications. We just got a paper back rejected where somebody said, no, what you write there, it can't be true because MPI can't be beaten, essentially. We just did a comparison between a new implementation using parallax and a common implementation with MPI. Our implementation was 10 times faster and more efficient and scaled better. And the paper, the comments from the reviewers were, no, that can't be. You did something wrong with the MPI implementation, which is complete nonsense. But that tells you that the community is very entrenched in the current way of doing stuff on their computers and on the current way of writing applications, that it's very difficult to convey the idea that everything has to be overthrown to get rid of the four horsemen. Well, I'll skip that. Just if you're interested, we can talk about the architecture of HPX. I am not going into that in more details. Let me give you a couple of results and then I'll show you a couple of graphs, and that's it. So what we did over the last months is that we had a first and formal release of our software, HPX. It's version 0.6, so it's a very early experimental version, but we expect to have a version 1 scheduled to be released in May. We re-implemented a lot of stuff in our system to make it more efficient. And what's the best thing is we have first very encouraging results from large-scale distributed runs on real clusters. A lot of detailed information, but the most interesting probably is that we have a couple of new applications in the works where we want to try out the ideas in other application areas like linear algebra, n-body problems, chess, and so on and so on. Okay, a couple of graphs, and let me explain what's going on here. AMR is a system where a way of calculating or simulating a physical system where you increase the precision in certain areas of your computational domain when needed. Black holes, for instance, when you simulate black holes, they are so far away, and but on the other hand, you're interested in getting some response and some analysis of the gravitational influence of that black hole, which it might have on Earth, to measure the gravitational waves emitted from there. Theoretically, you would have to model all the way from the Earth to that black hole, but the actual physics is happening just around the black hole. So you don't want to have a high precision in the main. It's just vacuum, right? There isn't anything, but you are very interested in a high precision around the black hole. So you try to improve that precision around that black hole, or if you have two black holes which coalesce, you probably even want to refine around each of those. And that's what AMR is doing. And the classic implementation of that AMR using MPI shows this characteristic. Let me explain that. On the y-axis, you have the scaling. That means the speed up you gain when you add a certain number of processors to it. The colors give you the number of processors, and the x-axis gives you the level of refinement. How much more precise do you do your computation in certain regions of your computation. The more levels of refinement you add, the more precision you get, and the more work you have to do in that particular region. On the other hand, if you add more cores, like 20 cores, the orange line, the uppermost one, for 0 levels of refinement, if you have a unigrid, you reach around 12, 14 times speed up. And as you can see, as you add more refinement levels, the overall scaling capabilities of applications just drop down a bit, right? They go down. And that means the more refinement you do, the worse gets the characteristics in terms of scaling. On the other hand, you want to do much more refinements, which explains why those applications are so bad when it comes to scaling capabilities. If you look at the same graph with HPX, you see a completely different behavior, and that's the interesting part, even if you're not really happy yet with what we see, but the characteristic is completely different. Whereas in MPI, you see that the scaling behavior gets worse and worse the more refinement you add. With an equivalent HPX application, the scaling goes up. So the more work, the more parallelism you throw at HPX, the better the behavior gets. Well, scaling is one part of the picture. You might say you might scale good, but you still might run a lot slower. And that's why a comparison of the runtimes. This gives you the ratio of the MPI code to the HPX code. That means MPI is roughly 2.5 times slower than the corresponding HPX code in wall clock time. So not only the scaling is better, but the runtime efficiency is much higher if you apply these characteristics. That's another interesting thing. I think Ram mentioned granularity control, right? You can control the amount of work to do before you check your email. And the more work you do, you might be able to do a lot of work in that time frame, but you can't wiggle around. You can't react to the request your boss might send you, right? So there has to be an optimum. If you check your email all the time, you don't do any real work. And if you check your email once a day, your boss might not be happy with you. And that's exactly what we see here. If you have a very small grain size, so you check your email every 3 seconds, your overall response time will be just go through the roof. You require a lot of time to get the work done. On the other hand, if you check your email only once a day, you might get work done, but not really. If you add to the picture that you might do 48 things at the same time, then you will get exactly what we are seeing with HPX, that there's an optimum in terms of grain size of amount of work to be done in one step, depending on the parallelism. And the higher the parallelism, the more, the better you see that minimum, right? That the lowest line is the most parallel one. And if you do only one thing at a time, it doesn't really matter how often you check your email. And that's very interesting because that's something you can't do with MPI easily or with common programming models. It's very difficult to do varying grain sizes and even adapt to varying conditions like system load, power constraints, and so on and so on. I'm done. It's almost the last slide. What I wanted to show is if you use that optimal spot, you can reach overall scaling behavior, which is much better than the corresponding scaling behavior of some application which is written with OpenMP, so with conventional ways. What you see here is a small Gauss-Seidel solver applied to a 4 million, 2000 by 2000 matrix. And the optimal grain size is 90 by 90 roughly, and you get a lot better scaling there. Just very quickly, that's some scaling graph when you do distributed runs, so that works quite nicely with HPX as well. And to wrap up, do we have a cure for these performance impaired applications? Well, I personally am not sure yet completely, because we're only halfway through in implementing all our ideas. But we already have very promising results on multi-core systems, and we have the first promising results on distributed systems where you use really clusters. The good thing is that no matter where you run your HPX application, whether it's on a single core or on a multi-core or on a cluster, your code doesn't have to be changed at all. It adapts to the environment. I told you about these current projects we are doing, and that's my last slide. Just as a summary. As it turns out, the parallax execution model can be implemented without adding significantly more overhead than MPI does, which is very important and one of the major results we achieved so far. The load balancing capabilities, which are intrinsic to HPX and to parallax, help to make AMR simulations it's highly beneficial for AMR adaptive mesh refinement simulations. And generally, there are regimes and applications that can really benefit from a very highly parallel model of computation. The last thing I mentioned, that runtime granularity control is very beneficial. And we think that these results are really very crucial, and they will help us to develop our applications in the future. Okay, thank you.